that the probability density function of the noise or of the impairment, which is affecting the measurement of data, then you can model it. And now the way you model, define the estimator. So in that way the estimator is better shaped to the problem. Now, it might happen that you don't know anything about the problem. For instance, it's quite typical that they give you data and you probably turn off that. I don't know. Thanks. Oh, good. It's for you. So, and for the moment, right? It goes on YouTube, right? Yeah. My nephew, went to YouTube and saw me, and then he said, and then with my account. Then I said, okay, I like, because the more I like it, the better it is. I said, don't do it. With my account. Anyway, so, and sometimes, you get the data, you know the generation process, so you know the model, but you don't know what is the model of the noise. So it's a set of data that are surely affected by noise, because data are affected by noise, and we discussed about what is noise. Noise is, is everything that is not accounted by the model. So, perhaps it's not really noise, but it's not something else. Like in the workshop that you did, it's, oh, by the way, have you seen the homework number 1? Okay. Easy, huh? Okay. So, and, so, by the way, so for instance, you have an interference coming from another place. And so that interference you can model, but perhaps after you understood its interference. The first time, you don't know what is that. So, what you do at the first sight? What you do at the beginning? You got the data, you say, usually you are called to give an answer. Oh, sorry. So you are called to give an answer to a problem. So they give you the data and then say, process that. Define, find the parameter. Now in this case, the preferred method is the so-called least square. So what is a least square? You essentially say that the set of data are modeled as a certain, function, which is S, okay, depending on the parameter P. That's it. So given that, the most intuitive way to make it is exactly the one where we started with. Do you remember? We set the error and we made the sum of the square of the errors. Okay? So according to that, this means that, what we can do is that we can define the least square, the least square function. So the least square function, which I write it compactly, is written as x minus s depending on theta transpose time x minus s theta. And you know perfectly well that this is representative of summing to thick. Is a sum on every I of x, I minus s, I depending on theta. Okay, and then you make the square for that. So what I'm representing is the sum of the square of the errors. So this is the metric I'm considering. And then my goal is to find a minimum for that. So this minimization is called the least square method. So what we started with, do you remember, the problem we started was with stocks, right? Okay, and so, the problem of predicting stocks, okay, can be, we frame it as a least square. We did not know that the name was least square, but it was very intuitive. By the way, it was so intuitive that I started with that, and nobody of you claim, but you know, what is this? Are you sure that is the best I can do? Okay, so it's really the most intuitive. Now, so this is the optimization function. So you know, I minimize the least square function, the objective function, and coming from that, I get the least square estimate. So the least square estimate is the argument of the minimum, so it's obtained by minimizing the least square function with respect to theta. Okay. Now, so what is a least square? You know, essentially, more than an estimator, is a numerical procedure. Because in many settings, you know, since we are not using any stochastic model on describing what is the noise, what is interference, what is here, what is that, since this one is the first site method, which is the first method that you do implement, okay, when you don't know anything. Huh? And then, I mean, it's the method where you implement to minimize, you design to minimize these objective functions, which is a least square function. Now, so the method itself, more than an estimator method, is a numerical optimization function. And so, you know, if it is easy, you can find as a quadratic form. If it is complicated, then perhaps, you know, you can implement, or you need to implement more sophisticated methods to minimize that. Now, so an alternative is to use the weighted least square. So the weighted least square means that, you know, when I write in this way, okay, so I say that I sum the square, okay, but you know, I sum the square of the error, but there might be some of the samples that are clearly more noisy than others. For instance, you have a set of samples, and you know, there are a few samples that they are really the outliers. Outliers means, you know, you have a couple samples that looks like they have nothing to do with the data. Just to illustrate the point. Assume that, you know, we are making the polynomial regression. Okay, so we have the samples here, I. And we have xi. And we have this set of data. And you know, I mean, given this set of data, there is one sample that is placed here. So clearly, all the data approximately goes here. And you know, this sample might have some spike in noise, big noise. Okay, noise effect. So how can I write a least square? Now, if I write the least square, the conventional one, if I write the conventional least square, probably if I make a polynomial fitting, like a quadratic fitting, okay, which means I'm fitting a parabola on that, perhaps my parabola might be here. Probably is here. Okay. Now the reason why the solution, which is the estimate, the solution of the problem of minimizing the least square is because, you know, in the least square function, if you look at, you have a sum, okay, on every sample, fine. Then you have I have error I squared. Okay, where error I is xi minus sit. Now you know this error is acting as a pooling element. So you know what's happening is that every sample is like a pulling with a spring, you know, in that direction. So I have a spring here, but you know. I have a spring that, since it's far away, is pulling a lot. Because remember, you know, is pushing with a quadratic. So since it is quadratic, if I have an error, and this error is, I don't know, is 10, and the other are 0.1, 0.2, 0.3, 0.1, blah, blah, and the other is 10. So this error equal 10 is pulling along, because, you know, the pulling effect is 10 to the square, which is 100. So, you know, this sample counts a lot. Counts on least square more than others. Okay? So, you know, since it's about that, blah, 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 since it's about that means that that sample, which is clearly bad sample, you know, is pulling too much. Now, let's apply a slightly different way. So let's define the weight of this square. Now, what is the weight of this square? The weight in this square says I'm summing on I a weighting factor Wi, which is positive, time epsilon I squared. Now, this weighting factor, if the weighting factor is close to 0, means that the sample practically is not contributing. And by the way, if you put it to 0, you know, you can take it away. Okay? If that sample is 1 or big, that means that that sample counts a lot. So, how would I design this sampling in this case? You know, I would make the sampling in the following way. So I will make, you know, all the sampling here at W1, W2 that are close to 1. Okay? And the sampling here, Wi, I will make it close to 0. Okay? So in this way, I might, for this specific experiment, distribute the weights, these are the weights, okay? Distribute the weights as if they're approximately, or let's say all 1, except this sample that is going to 0. So what am I doing? I'm stripping a sample. So between stripping means take it out, okay? Between stripping the sample or, you know, considering it, but, you know, don't give too much importance. So between black and white, there is also the gray part. And so I can choose W, which is the weighting factor, to be dependent on the specific sample, and I mean weight or underweight that error according to the quality of the data that you experience. Okay? Like, I mean, this is clear, but there are many configurations where it's not that clear. Now, if I make it this way, okay, so perhaps what I expect that my new quadratic fitting is going this way, which makes more sense than the dashed line. Okay, so this is by Wi. Okay, so how do I write it? You know, I mean, I would say it's kind of easy. I write in the weighting factor in the following way. So, you know, I can write a j theta, which is the objective function, which is x minus s theta, which is the error vector. Okay, I make a transpose, fine, but then I define, you know, a matrix W that is placed in the middle. Okay, here I have x minus s theta. Okay, so this is the vector of the error, transpose, and then this is the vector of the error. Now, if W is diagonal, then, you know, I'm weighting each entry depending on the quality of the data. Okay? Now, is there any rule? No, there is no rule. But is it optimum? Well, I can say that this method is optimum in one special setting. Is it clear up to now? You know, so you know, it's much intuitive. Huh? Now, so the question is, you know, how optimum is this weighted least square? Now, if I look at the shape, the shape of the objective function, remember, I need to minimize that, okay? So if, you know, if the error, if the noise superimposes Gaussian, if W is chosen to be the inverse of the covariance matrix of the impairment of the noise, then in this case, least square coincides with the maximum likelihood, and it is optimal. And by the way, it reaches the primary outcome. So I say it again, which I believe should be written here. No, it's not written. I have this sentence. Okay, so this is what I was mentioning. So, you know, if I'm considering that the noise is Gaussian, okay, so, you know, if the noise is Gaussian, so for Gaussian noise, the weight of the square coincides with the maximum likelihood, and by the way, if the problem is linear, coincide with the error is equivalent to the Cramer-Rao, only if I choose the weighting factor to be equal to the inverse of the covariance matrix of noise. Now, this effect is very important because, I mean, it's giving a lot of relax when I implement the method. So, in other words, when I implement the method, I start weighting, you know. So on the data, I weigh, I say, okay, that sample doesn't count, this one, okay. So I iterate again, it works in this way, huh? So you iterate again, you see the fitting, okay, it seems that, you know, the error is pretty stable now. And so, I mean, then you start reasoning and say, okay, so what about if I can now, based on this model, I can see, I mean, what is the noise, if, you know, if the noise is Gaussian or not. Then you make some test of Gaussianity on the residual, and then you see if, you know, the residual, which should be the noise, is Gaussian or not. Then if that one is Gaussian, then you go back to the data, you impose the W, which is the weighting factor, to be the inverse of the covariance matrix that you get. So, you know, this is giving a lot of safety, is giving a lot of relax when you apply the method, because you have a proof of optimality, okay? Now, once more, this is the concept of diagonal weighting matrix that we just discussed. Sometime, you know, in the data, you put some memory. And this memory is, you know, is important because imagine we are making the prediction of stocks. And in making the prediction of stocks, I mean, I'm using the data, but, you know, I cannot use the data from 3 years ago on the stocks, okay? Because, I mean, yeah, they have an influence on today, but, you know, it's not that much. So, in other words, once again, in our experiment, okay, we have our samples that are moving a certain way. I have a sample that is, I mean, perhaps I don't have an outlier, blah, blah, blah. And then, you know, I want to predict the sample here. Okay, this is the example of stocks. Okay, so I want to predict the sample here. And now, in order to predict, you know, I'm using the data, all the data that I have. But you know, the data, this is today. The data of yesterday, which is the stock value of yesterday, is more important than the stock value of 3 years ago, or 10 days, or 5 weeks, okay? So how can I introduce a kind of memory, which is, you know, is weighting the data according to the time, to the position, to the position of the sample. Now I can introduce a weighting factor. This is the weighting. which is, contains a so-called exponential forgetting. Now, the exponential forgetting is saying that if I consider lambda as a forgetting factor, here the first one is this is the weighting. The first one is lambda to the power of 1. The second one is lambda to the power 2. The third one is lambda to the power 3, and so on. So I'm introducing this lambda as a forgetting factor. Now, if lambda is close to 1, what I have is that, I'm not weighting anything. Because when the lambda is ideally equal to 1, okay, then, I'm weighting everything with the same weight. If lambda is very close to 1, then, I'm weighting the recent more than the past. So if lambda is going to 1, I get a so-called infinite memory. Because I'm not weighting anything. Okay? If lambda is very much smaller than 1, then I have a short memory. Because if lambda is equal 1 or similar to 1, lambda very big, let me say lambda close to 1, then the weighting factor is almost 1, at least for a neighboring point. If the lambda is very small, let's use this color. If lambda is very small, then I'm weighting the first, the second sample, then the third, fourth, but then after that I forgot the impact of the far away sample onto the present. Now, how do I write that? Tell me.
If lambda is 0?
If lambda is 0, I'm not weighting anything. No, I'm not predicting, I'm not weighting anything. So that means I'm not doing anything. So lambda, writing formally, okay, lambda is larger than 0, smaller or equal 1. This is the analytical condition of lambda, okay? And lambda is is a forgetting factor. So analytically, is it clear?
Yeah.
So analytically it stands in the following way. So my objective function J is obtained by summing. Now don't be faked by the lambda. So it is lambda n minus I. The reason why is the lambda n minus I, because I start from n. So when I is equal n, I have lambda to the power of 0, which is 1. Okay? If I is equal n minus 1, it is n minus 1, which is lambda to the power of 1. And so I'm down weighting starting from n. Okay? That's the mean. And this is the usual error. Error to the square. So for lambda equal 1, no weighting and infinite memory and blah blah. Small. There is a fade on the leaf. Convenient. Convenient in case we are dealing with something that is changing. Convenient when we are dealing with something that is non-stationary. Something that is changing in time. We will discuss that. After the test next week. Okay? About the main motivation of the explosion of digital signal processing is because in digital signal processing you can manipulate non-stationary signals, and light is mostly non-stationary. For instance, during the lab you did, during the workshop you worked with the audio signals, and they had some silent part, right? Okay, that silent part, if you look at the definition of stationarity, silent does not exist, because silent is not included. So that signal is not stationary. You did not ask yourself, is it stationary, not stationary, okay? And you naturally sliced, segmented So it's kind of very intuitive that when you have a no stationary process, you cut it in pieces of stationarity. So where inside of that cut, you have the random process that is stationary. And stationary might be that at the side, the signal is silent. Okay? So you have seen sliding under the carpet, which is your brain carpet. Okay, we slided the concept of no stationarity without giving too much emphasis on that. Clear? So and in this case, when you have the no stationary signals, and you need to process the data from no stationary signals, then in that case, you need to introduce something like which is taking into account that the data is changing and fading, and the forgetting factor are two privileged methods. We will see later, so during the semester, after the exam next week, okay, we will see that there are one method which is based on least square and which is updating the least square solution by introducing a forgetting factor. Similarly as that is exactly that method. Okay, so it's only to recognize this method framed in this way, and it's a very useful method which is called recursive least square, and it is used for specifically treating non-stationary signals. And this will be part of the homework too. Okay. Now skip it. Order of adaptation. Skip it. Order of adaptation is. I tell you in a word so that if you're interested, you look at it. Order adaptation means assume that and by the way, I have an exercise on order adaptation for you. But order adaptation means assume that you are estimating a linear regression. Assume that you have a set of points. These are experimental points, okay? And actually, you don't know if these points are how these points are modeled. So you get this set of values, experimental values, and you know what is that. So what you do, you start with the linear. And you say, I assume it's linear. And then it goes this way. Now, someone is telling you, but why don't you try as a quadratic? Then what you do is, you try with a quadratic. What is the difference between linear and quadratic? Linear and quadratic, the major difference is the following. In linear case, I am modeling the data xi as equal to a plus b times I. This is the linear case. But the quadratic is plus ci squared. Okay? Now, even if apparently I'm simply adding c there, the estimated value a and b depends if I use a linear regression or if I use a quadratic regression. And so that means that what I'm doing is that I'm increasing the order. So the order here means that I started with the linear and I'm increasing the order to the quadratic. Now, you can imagine that this is not just a very toy example like a linear quadratic, but you can imagine it's a filter. So I start with a filter of length 15 and I want to get the coefficients of a filter length 16. So, what that means that I go from 15 samples to 15 plus 1. I'm increasing the number of unknown plus 1. So, when I increase the number of unknown to, I augment the number of unknown and the number of parameters to estimate plus 1, I would like to estimate the additional parameter by benefiting of all the estimate that I did with the first 15 samples. Now, the way to make this least square estimate is by increasing the order and adapting the order and, you know, increasing the order 1 plus 1 plus 2 plus 3 and so on without recomputing everything. Now, it's not a trouble if you consider that you have a very small problem. Imagine you need to repeat the problem many times. You are searching for the solution for that. Then you know you need to make a lot of computation. And you need to be computationally efficient. Now, rather than discussing this, I will make on C exercise. Okay, you can read it, it's here, but you know, we will see on with exercise. Last, which is left out, is the so-called robust estimator. Estimation reward estimators. What are robust estimators? Now, usually, you know, intuitively, the least square is based on a metric, and the metric is quadratic. So I take the error and I make a quadratic of the error. So the square of the error is the sum of the square of the errors. This one is intrinsically optimal if, you know, the noise is Gaussian. So now there is a pairing between the noise model and the estimator. So if the noise is Gaussian, then you know the function to optimize is quadratic. Okay, now, but what about if the noise is non-Gaussian? And now you know the function to optimize the optimum would be not the quadratic. So what about if I like to use the quadratic? Because the quadratic is convenient. People like to use the quadratic because, you know, by the quadratic I write the quadratic form, and then I get the closed form solution, or similar, okay? Now, in order to manipulate problems where, for instance, the data are departing from the Gaussian assumption. And this happens when you have outliers. So outliers are, you know, these are samples that are clearly, this is the sample, this is the sample, okay? So imagine that, you know, you have these, your data, and there is a couple of 2 more, 3, 4, 5 samples that are out of the distribution of the data around, for instance, this model, which is the solid line. Now, you know, these are outliers because are generating an error that is very big. Now, what to do in this case? Now, option number 1, we saw it. I take this sample and I downweight. I put a weighting factor to be close to 0, which means I take this sample out. Okay? Now, you know, in some cases, finding the outliers is very easy. So, you know, I can visually see that these 2 samples are out. But in other cases, you know, it's not that simple to see where are the outliers. Because, I mean, you got the data, and these data are multidimensional. It's not simple like that. You have 2 dimensions, you know. You need to consider that you have a multidimensional data. Imagine you need to make a multidimensional classifier. You have a set of data coming from, I don't know, from sex of the people, coming from, what the habit of the people, how many clicks the people makes on this picture, how many clicks makes on the other, blah, 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 blah. So, you know, my data is really, really growing, okay? Now, in that case, it's not easy to spot the outliers. So, what are the other way? The other way is that, you know, what is a mistake? Now, the mistake, if you think about it, is that we are assuming that the quadratic is the best that we like to treat. So we like to manipulate the quadratic function. Now, you know, and we know that if there are outliers, these outliers is because the data are not affected by Gaussian noise. They might be affected by a noise that has the so-called long tails. We discussed about the Laplacian noise, right, in the past. Now, so, you know, the Laplacian, you know, if you look at the difference between Gaussian and Laplacian, why the Gaussian distribution is smoother than fine, the Laplacian for the same power is exponentially distributed. Okay, so if this one is Gaussian, this one is Laplace. But you know, that means that in Laplace distribution there are, with high probability, samples with large amplitudes. So, you know, Laplacian distribution are affected by large samples. Okay? So large samples means large values. Okay, large values are more lucky. Okay, now we'll see that in this case, in the case of Laplacian, the maximum likelihood method includes the minimization of the absolute value of the error. So, in case of the Gaussian, okay, the optimum function is the minimization of the square of the error. In this case, is the minimization of the absolute value of the error. So, you know, that means that in the first case, in case of Gaussian, my function, which is taking the error, is quadratic. In the second case, my function, which is, defining the objective for minimizer, is absolute value. So, in the first case, for Gaussian, so if I have an error, epsilon I, so for Gaussian, you know, this behavior, this is epsilon I squared. And for Laplacian, is this one. So I have two objective functions that I'm manipulating, the Gaussian and the Laplace. Now, how do I treat these, these outliers? I treated the outliers by so-called robust estimation methods. Robust estimation means that I try to use the conventional least square quadratic function, or I manipulate my quadratic weighting function in such a way that I can still use all the theory dependence. Which means I move it back to the quadratic behavior. Now, so recalling this aspect that Laplace is related to the L1 norm. The L1 norm means, I'm taking the absolute value of the error, while the Gaussian is taking the square of the error. Okay? Given that, I come to the way to handle the estimation in case of outlier. So the robust estimator is simply redefining the objective function with a certain phi, where phi, is a penalty, and this penalty function is quadratic in case of Gaussian, is absolute value in case of Laplace. In other words, is Gaussian in case there are no outliers, and is absolute value in case there are outliers, because outlier means that I have a big amplitude with perhaps, non-negligible probability. But big amplitudes are outliers because are very big for the Gaussian distribution. For the Gaussian distribution, I don't expect big amplitudes. And so this means that, I need to shape my penalty function to take into account of these two behaviors. Now, so this is the same, then let me just map it back. So in case of Gaussian, phi phi is equal to epsilon squared. In case of Laplace, phi epsilon is equal to absolute value. Okay? Now, if it is a Gaussian, very happy, because if it is Gaussian, then you know I have epsilon squared, I know everything. If it is the absolute value, then it's a trouble to optimize. So if absolute value, which is if assuming that I have a Laplace distribution, like for the outlier, that is complex to optimize. Now, what are the different options? People have been working and is currently working on a robust method because Gaussian model is not always applicable. And there has been a lot of activity on defining the possible estimators. Now the possible estimator is a sketch here. This is the function I'm considering. So look at, there are multiple functions here. Now, assume that the noise is Gaussian. My penalty function, if Gaussian, is quadratic. This is the quadratic one. So, if, let me write blue, so if Gaussian, the penalty is quadratic. Now, but if I have a big outlier, what I can do is that I can saturate the error. So another option is that if my error is very big, then I simply saturate its value. So my new penalty function is quadratic within the interval, a certain interval, plus minus. And then is saturated, which means that the outlier is not weighting a lot, is not counting too much, because the degree of counting for the outlier is saturated by the penalty. The third possibility is that my penalty is a mixture. So it is quadratic here up to a certain interval, and then it's linear after the interval. What does it mean? It means that my penalty is quadratic when the error is very small, which means within this interval I'm using the Gaussian model. Outside of the interval I'm using Laplace. Now, if my penalty function is not linear, but is shaped like this, I don't have a closure form. I cannot find a closure form. So, this means that the robust methods are intrinsically iterative. Robust methods are, first of all, look at here. This is based on the finding this interval, plus minus L. Who is giving me this? By trial and error. I can use different shape, different weighting, or different, function. Which one to choose? I can start with the quadratic first. I can see that the quadratic is Gaussian. I can notice that the quadratic is really, in some cases, is not giving the right answer. Then I say, okay, probably, there are some outliers. Okay. So if there are outliers, what I do is I try to limit the impact of the outliers, or I saturate. I start with this saturation effect. Then the saturation is giving me the wrong answer. So that means if I have the outlier here, making the saturation is equivalent to constantly put this sample here. This is the effect of saturation, because the error, is reduced to a constant value. Now, But I mean, saturation, this is saturation. Saturation, you know, is pulling the sample to the boundary, which is plus minus L, the boundary. But I mean, this means that if this sample contains some information, for instance, you know, if I have a lot of data which is shading that way, but you know, I have another set of data that is shading on the other, like imagine I have a set of, and by saturating, I'm losing this component of the information because I'm pulling all these samples to be equal to that. Okay, so I'm losing content, and it's not right. So what I can do is I can take these samples that apparently to me, for a quadratic model, for a Gaussian model, they are outlier. I consider them as outlier belonging to a different distribution, which is Laplace. Then in this case, you know, I can use a different weighting function, which is this one. These are piecewise, quadratic, and linear. Now, there is not a unique solution to that. It's just by trial and error. It depends on problem by problem. There are a lot of literature on that, okay, which is now squeezed in a few sentences here. And I encourage you to give a look at in case you face these kind of problems, which is where you don't have a Gaussian, we don't have a non-quadratic, you don't have the data that are nicely clustering along I don't know, a line along the point or whatever. If you have some data, then you have few samples far away. I mean, those few samples, they might tell you something. If you are looking for anomaly, those samples is what you look. Okay? So, as I said, I'm not giving you the solution, I'm just giving you the tool. So, these are the analytical expressions. So, robust saturation penalty, which is the one that I was describing to you, which is, is quadratic, then is a constant. Another one is robust outlier stripping, which is this quadratic, but if it is too big, then I strip the sample. Now this is equal, this is the equivalent, to making a weighting factor that is equal to 0, which means if a sample is too big, then I take that sample and I strip away. And the last one that I gave you intuitive description is the so-called Uber robust estimation, which is the behavior is quadratic in the lower part around 0 and is linear far away. Now, let me give you, since sometimes you get the distribution, you don't know what to do, let me give you a very simple way to understand what is the process you are treating about. Assume that you have, this is the practical insight. Assume that you are making your experiment. You start with you start with a quadratic. Okay. Now, when you start with a quadratic, then you come out with the first solution because you don't know if it is nonlinear, if it is Laplace. You don't know. You know nothing. Okay. And so you get the data, and you start with the quadratic, which means you make the least square estimate. Okay. Then you get the theta hat of least square. Okay. Now, what you can do is you regenerate from this one the data, which means you get as theta hat least square, and then you can calculate the error, which is x, the vector of x minus s theta hat least square. So out of that you have a big vector. Imagine you are with a big set of data, big data. Then what you can do is, why don't you look at the histogram of this error? Don't be shy. Look at the data. The data are telling you. You can learn from data. A clear, a very wise observation of the data is telling you much more than more theory. Of course, you need to have the theory on your backpack. Okay, so you have your back and you have the theory in the back. That means that every time you are moving in one direction, you know what you're doing. So if you look at the profession, it keeps moving. So it seems that it's making trial and error. So it's trying this way, then it's going back. It's trying the other way, it's going back. It's trying the other way, it's going back. Then it's take this and that, push together. Okay, these steps are carried out because in every step you have a very clear view of what you want to do. Let me start with a very stupid one. If I have this epsilon is affected by outlier. Because if this is the error, and this error is the one that I get because I made a least square. But it might be affected by outlier. So how can I see what model to use? So now this is my suggestion. Imagine that the data is very big. So-called big data. It's a pleasure to have a big data because you can do everything with a big data. Everything means you can get the histogram. You can make you can look at if the histogram is behaving in some way or another. Now, so let's make a histogram. Make a histogram of epsilon. If I make the histogram of the epsilon, I don't see much. Perhaps I see that this histogram is having some behavior, looks is a bell. Then you say, oh, Gaussian. Wait a minute. Make the log of the histogram. Why am I making the log? So I take this scale and then make the logarithmic of this scale. Remember, it's not the histogram of the logarithm, it's the logarithmic of the histogram, okay? So, if I make the logarithmic of the histogram, what do I expect? Now, I expect the following. If the PDF is Gaussian, okay? Remember, Gaussian means A minus epsilon squared divided by something, okay? Now, if that one is Gaussian, I calculate the logarithmic for that is equal to minus epsilon squared divided by blah, blah, blah. Huh? Now, if the PDF is Laplace, Laplace means A minus epsilon divided by something. Okay? Now, if I make the logarithmic, this is equal to minus epsilon divided by something. Okay? Now, let's make it. So what I expect from that, I expect that this one has a parabolic behavior because this is the logarithmic of this one. So if I make the log of this, I can see a nice parabola, right? And the aperture of the parabola, the curvature, depends on sigma. Okay? I'm telling you, this is the practical side. Okay? So that depends on sigma. But what about if when I make this plot, I don't see a nice parabola, I see something like this. Now, if I see something like this, that means that it starts to be linear here. That is the Laplace, which is dominating. So, here, for large amplitude is Laplace. And for small amplitude is Gaussian. Isn't that the same of Huber, robust estimator? So Huber, robust estimator, is essentially trying to, or trying, making, estimating a set of parameters, like considering that in the neighboring of the solution, the distribution is Gaussian. For far away, it's not Gaussian, so it's I use a weighting factor that is linear. Then I'm assuming it's their Laplace. So the slope, now you can make a nice exercise. So the slope here depends on the parameter of the Laplace. The curvature here depends on the sigma of the Gaussian. And by the way, you have also this nice crossing point. Look, when the behavior is going from quadratic to linear. So nice. I have this point where the curvature in log is changing. So I can find where, what is the limit, where to use the Gaussian, where is the limit, and where outside of that to use the Laplace. So I simply do by taking the data. Histogram, log, is linear, is quadratic and linear. Okay, so since it is quadratic and linear, then I need to use Huber robust estimator, because the linear part is highlighting that there is a Laplace distribution underneath. Okay, this is one example. I try to remember. Let me write some practical comments. Okay, and I conclude with everything for the exam next week. Now we do the exercise. Do you need coffee? If you need, no more than 5 minutes, otherwise I continue. You need? You need that. I saw you. Okay, 5 minutes, please.